So in this investigation, we're going to see how you can use probability along with mathematical models to create simulations that will help you predict the future. So just a reminder, the probability that an event will happen is the number of times the event occurs divided by the number of trials. Right? So for experimental probability, you actually have to try something a whole bunch of times, and then you see how many times the event you want happens. For theoretical probability, you investigate the event and try to figure out from looking at the event what the probability will be. We already saw that there's lots of times when you cannot do theoretical probability. All you can do is experimental probability. But there's a problem. What happens if you have an event that occurs only once, but there's no way to find the theoretical probability? What do you do in that case? For example, I'm only going to retire once. I have to save enough money so that my money will last through my retirement. Now I went to my financial planner, and she says that there's a 97% probability that my savings will last through my retirement. Well, what does that mean? How can she figure out that there's a 97% probability without my actually retiring a whole bunch of times and figuring out how many times I was able to keep my money, I was able to have enough money to retire on? Here's another case. Imagine that there's a hurricane in the Gulf of Mexico. The hurricane is traveling towards Florida. What's the probability that that hurricane is going to cause devastating destruction in Boston? We can't run the hurricane a whole bunch of times to see what happens. So what do you do in that case? How do you figure out the probability? You can't run the experiment, and you can't figure out theoretical probability. So one way to answer these questions is by creating something called a simulation. A simulation is a model that allows you to find an experimental probability when you can't work with a real situation. So I'm going to give you a time to find your vocabulary document and add that definition to your vocabulary document, and then we're going to take some time to look at some more examples. So here's a new example. You want to train a new pilot. You want to know what the probability is that when that pilot takes the plane up into the air, that the pilot will not crash the plane. Well, okay, you don't want to have the pilot go up in a real plane and fly it and see how many times the pilot crashes the plane. That would be expensive and dangerous. So you use a flight simulator. The pilot goes up in a flight simulator a whole bunch of times until they don't crash the plane anymore. So that's an example of using a simulation. Here's another example. You want to know what the effect would be of a bomb or some sort of nuclear blast in New York City. So you don't want to drop a bomb in New York City to see what happens. You use a simulation to see what could happen, and then you can make predictions and you can decide things about evacuation and things like that if you are the governor of New York, if you are the mayor of New York City or the governor of New York State. So what a simulation does is it uses mathematical knowledge and then uses probabilities to predict what would happen. So rather than running an experiment, you create a simulation that effectively runs the experiment on a computer or using some other technique. And we'll talk about some techniques next week. For now, we're going to sort of think about simulations that run on computers. So I'm going to give you an example of a simulation that I had something to do with. So you guys have all heard about climate change. It's a big topic right now in terms of how greenhouse gases affect the climate on the Earth. So climate change science started happening in the 1980s when a number of scientists had this hypothesis that the use of global gases would cause a sort of a greenhouse gas effect on the Earth, and they wanted to know how that would affect temperature. They thought that it might cause the temperature in the Earth to go up. So what they did, there's only one experiment, right? The time is going to go by once. But what they did was they created a simulation, actually they created a bunch of simulations that modeled the effect of carbon gases on the environment and on climate, and then ran the simulations a whole bunch of times. In fact, full disclosure here, my very first job when I graduated college was to work for an economist named William Nordhaus, who was doing this kind of economic and climate modeling using very old computers. I was one of his computer programmers, and my job was to take his models and to write computer programs that could be run to see what would happen in the future. So this was back around 1982. So this is a graph from somebody else who was doing some of this work to see what was going to happen with fossil fuels and how they might affect the environment. So I'm going to focus now on this graph. You can see on the x-axis of the graph you have the dates, which starts in 1950, and this is actually the present when the graph was made. So this was 1980 or so. And this data here is actual data from observed climate. So this is all stuff that's real. So I'm going to highlight that. This is what this person knew coming into it. And everything past that was that person's projections as to what would happen with temperature. So here's temperature on the y-axis. 0 is the baseline. That was the temperature when he did his study in the 1980s, and this is the temperature in Celsius increasing by 1 degree, increasing by 2 degrees, etc. And what he found, or his model said, was that in the future, for him, that temperatures would increase, and then depending on what political decisions we made around, this is actually around 2010, 2020, temperatures would either increase faster or not increase faster, but there would still be this increase. So again, these results are based on a mathematical simulation, a model saying what will happen in the future from this point on. Now the cool thing is that we are now in 2020, and somebody went back and looked at this person's predictions, and the pink over here represents the actual temperature, observed temperature from 1950 up to the present day. And you can see that this mathematical model actually did a pretty good job of predicting what was going to happen in the future. So now I want to show a video of a use of mathematical models and simulations for predicting the path of hurricanes.
We model old storms because it gives us a way to compare the simulations to observations and try to assess the physical processes within storms and also how well those processes are represented in the forecast models, because that's key to improving forecasts in the future.
With improvements in computing power, researchers have been running ensemble forecasts.
Instead of a single forecast, we run a whole series of forecasts where you make slight variations to the initial information that goes into the models and then see how much spread you get within those forecasts.
Running ensembles gives us a visual description of the level of uncertainty associated with forecasting tropical storms.
And the average over all those ensembles usually gives you a better forecast than if you ran just a single forecast model.
One way to test forecast models is to reanalyze past storms.
It's very important to study the worst possible storms in history because those are the ones that really put the system to a challenge.
NASA and NOAA cooperate in satellite systems and sharing data, as well as experiments and modeling research, all of which enable NOAA and other agencies to provide better forecasts of tropical cyclones.
When NOAA, National Hurricane Center, issues a forecast, the better the forecast is. Historically, the more likely is that people would trust the forecast, and decision makers will make the right decisions, and they will tell what place has to be evacuated and what place can stay.
To get a clearer look at the processes inside the hurricane, NASA's Global Precipitation Measurement Microwave Imager, or GMI, gives us an X-ray beneath the clouds.
If you have a storm that maybe isn't well defined, doesn't have a visible eye, with the GMI and similar instruments, you're able to see the rainfall structure underneath those clouds. So you can see the ring of heavy precipitation in the eye wall, as well as several of the rain bands. And that really helps to tell us a lot about how the storm is evolving and how that might relate to the intensity of the storm.
Representing those small-scale eye processes in global models has been an ongoing area of research.
By increasing resolution and increasing, of course, the quality of the physical processes representation inside the model, that all global models have been getting better and better. They make hurricanes that are smaller, more compact, closer to the real size, and the eye becomes smaller and smaller, and they become more intense.
So when we first started talking about probability, one of the things that I stressed was that the more information you have, the more accurate your probability will be. And I think with this video, hopefully you saw that as more information and more knowledge, we get more knowledge about hurricanes, then you can predict probabilities a lot more accurately. But the way that you're predicting them, or the way that you can't just predict them theoretically, what they're actually doing is they're making a simulation of how the hurricane will progress by saying, okay, here's the probability of each one of these things happening, and then let's make a simulation running the different scenarios on a computer or in some way to figure out what will happen in the future. So now that you know what a simulation is, coming up we're going to learn how to make very simple simulations, not using computers, but using simple probability tools like spinners and dice and coins to simulate some fairly simple scenarios where it isn't clear or isn't easy to figure out the theoretical probability.